7.2.6 Taub Fiber Analysis, Part 2. The metric has topology R times S cubed. See equation 7-35. See equation 7-36. Metric singular at t equals t sub plus or minus equals m plus or minus m squared plus script L squared. Raised to the exponent 1/2 end exponent, extending across these surfaces one arrives at NUT space. Before discussing extension, consider Meissner space. German M topology R times S to the first power G times ds squared equals negative t to the negative 1 power dt squared plus td normal psi squared 0 is less than or equal to normal psi is less than or equal to 2 pi, metric singular at t equals 0, and 0 is less than t is less than infinity.
German M German G can be extended by defining normal psi prime equals normal psi minus log t, the Courd. Trans. Utilized in any extension must itself be singular at the point in question in order that it may cancel the appropriate term in the metric. The metric becomes, see equation 7-37. Region T is greater than 0 is isometric to German M German G. Similarly, normal psi prime equals normal psi plus log t yields German M double prime G double prime, with ds squared equals negative 2d normal psi double prime dt plus t times d normal psi double prime squared. We have two inequivalent locally inextendable analytic extensions of German M German G, both of which are geodesically incomplete.
Locally inextendable. There is no open set German U. German is less than M with non-compact closure in German M, such that the pair German U German G vertical bar sub German U has an extension German U prime G prime, in which the closure of the image of German U is compact. Let our manifold German M be R2 with a closed disk removed. Metric Lorentz. Consider an open set which borders that disk, almost touching. The closure of script U is non-compact. By construction, it adjusts the edge of the manifold. The pair, script U script, G vertical bar sub script U, has the trivial extension, script U prime, G prime, in which script U prime includes the edge of the disk, thus extending on German W, and G prime is simply G of R2. The closure of script U prime is now compact. Such is an example of a space that is not locally inextendable.
Local inextendability is a stronger condition of extendability. It allows for a fiber bundle type extension of the manifold. Regular extension of German W German G simply asks that there be an isometric C to the R embedding mu colon German W German right arrow German W prime 4, German W prime, G prime. Now Meissner space is not simply connected, so let's study German M German G, German M prime, G prime, German M double prime, G double prime, in the covering space and see what is found. The metric for German M German G, see equation 7-38, which has Lorentz signature and is restricted to t is greater than 0. We only have two dimensions, so conformally flat. What is the coordinate trans? That yields ds squared equals negative dt squared plus dx squared ? Consider.
See equation 7-39. Then see equation 7-40. And see equation 7-41. See the group of equations. So we have found the coordinate transformation that shows that locally Meissner space is simply Minkowski space, i.e. Meissner space is covered by a portion of Mink, i.e. Meissner is flat with identifications. What is the rule for identifications? The identification involve the coordinate normal psi, where
see equation 7-42. Switching to see equation 7-43. We are able to work the domain 0 is less than or equal to normal psi is less than or equal to 2 pi more easily, and with the identification of normal psi equals 0 with normal psi equals 2 pi or normal psi equals alpha plus n 2 pi times with of normal psi equals alpha, t of alpha, x of alpha, equals t of alpha plus 2 pi, x of alpha plus 2 pi. Thus, see the equations. And
see the group of equations shown. Thus, Tx is identified with t hyperbolic cosine of pi plus x hyperbolic sine of pi, x hyperbolic cosine of pi plus t hyperbolic sine of pi. So one identifies all points. See equation 7-44. for all integer values of n. Since t is greater than 0, write double arrow t is greater than 0, and since t squared equals 4t plus x squared times th of en times the absolute value of x is less than t. Thus, German M German G is the region of Minkowski space in the future light cone, I of the origin with identifications as given. The space German M German G is thus the quotient of I8A by the discrete subgroup G of the Lorentz group consisting of boosts by multiples of a given factor.
The action of G in region I is properly discontinuous, as it is in regions I plus 2 and I plus 3. The fraction with numerator I plus II, 8A, and denominator G is German W prime, G prime, t is greater than negative x, from cylinder, and null geodesic picture. The fraction with numerator I plus II, 8A, and denominator G is German W double prime, G double prime, t is greater than x. The fraction with numerator I plus II plus III, 8A, and denominator G is not Hausdorff. The fraction with numerator m minus the set p, 8A, and denominator G is the maximal non-Hausdorff extension of German M German G. L. The fraction with numerator m and denominator G is a Hausdorff manifold.
The bundle of linear frames, i.e. the collection of all pairs x, y. X, y is a member of T sub q at all q is a member of M. Action of A is a member of G of On times M, induces an action A sub asterisk times On L of German W which takes x, y, to a sub asterisk x, a sub asterisk y, etc. The fact that the bundle of frames can be well behaved even though the space is not, suggests that it is useful to look at singularities by using the bundle of linear frames. Back to 4D Taub space, German M German G. As German M is simply connected, one cannot simplify matters by going to a covering space as was done with Meissner space. However, a similar result can be achieved by considering German M as a fiber bundle over S squared with fiber R to the first power times S to the first power. Bundle projection is defined by
pi colon German M German right arrow S squared such that T, normal psi, theta, phi, right arrow, theta, phi, the product with the t-axis of the HOPF fibering S cubed right arrow S squared which has fiber S to the first power. Recall that Taub space has a 4-dim group of isometries whose surfaces of transitivity are the three spheres open brace T equals constant close brace. The group of isometrics maps fibers of the bundle defined by pi into fibers, and so the pairs script F script G are all isometric, where script F is a fiber, script F script approximately equals R to the first power times S to the first power, and G is the induced metric.
The fiber can be regarded as the T, normal psi, plane, and the metric G on script F is obtained from G by dropping terms in d theta and d phi. See equation 7-45. So we have described German M as a fiber bundle, i.e., a bundle which is locally a product bundle, German N German times A, German N German pi. The usefulness of this is that while German M cannot be decomposed into the product manifold, R to the first power times S to the first power times S squared, it can be locally in terms of fiber bundles. An example of this, S cubed right arrow S squared, where the S to the first power fiber is not indup. Over S squared, it has continuity requirements. Thus, not a global product, but locally anything can be chosen and the rest of S to the first power over S squared adjusted to fit.
There are 4 killing vectors for any T space. See equation 7-46. No normal psi in equation, so every killing vectors lies in a hypersurface of constant normal psi. A, B, C are each one of x, y, z. Note, all brackets are Lie brackets.
See equation 7-47. The usefulness of the fiber bundle decomposition is clear. Just as R to the first power times S cubed is not a direct product of R to the first power times S to the first power with S squared and yet can be considered so locally, we find that the metric G is not the direct sum of G sub V and T squared plus script L squared times G sub H, but it can nevertheless be regarded as such a sum locally, where G sub V and G sub H are defined according to the following. The tangent space T sub Q at the point Q is a member of German M can be decomposed into a vertical subspace V sub Q which is tangent to the fiber and is spanned by the fraction with numerator partial differential and denominator partial differential T and the fraction with numerator partial differential and denominator partial differential normal psi, and a horizontal subspace h sub q which is spanned by the fraction with numerator partial differential and denominator partial differential theta, and the fraction with numerator partial differential and denominator partial differential phi, minus the cosine of theta the fraction with numerator partial differential and denominator partial differential normal psi. The Taub metric respects this local form.
See equation 7-48. See equation 7-49. See equation 7-50. See equation 7-51. Let's analyze the fiber bundle for Taub spacetime carefully, and switch to notation by.
See the equation. Becomes C equation 7-52. Decompose all vectors in the tangent space T sub q at q is a member of German M such that locally we have a direct sum of metrics for the corresponding direct product from the fiber bundle decomposition of the space. See equation 7-53. See equation 7-54. See
equation 7-55. Decompose the vectors of T sub q into two groups, V sub q and H sub q. The metric induced on the fiber is see equation 7-56. The vectors which span the fiber comprise V sub q, the set the fraction with numerator partial differential and denominator partial differential t, the fraction with numerator partial differential and denominator partial differential normal psi a and d times satisf of y g sub h of V sub q equals 0. The vectors which span H sub q should be such that g sub v of H sub q equals 0. So H sub q colon the set the fraction with numerator partial differential and denominator partial differential theta. The fraction with numerator partial differential and denominator partial differential phi minus the cosine of theta. The fraction with numerator partial differential and denominator partial differential normal psi. For such a decomposition of T sub q we have.
See equation 7-57. Or, with relabeling, see equation 7-58. So, given T sub q for q is a member of German M, we want to decompose T sub q into two subspaces. V sub q, the vertical subspace, which is tangent to the fiber, and H sub q, the horizontal subspace, whose projection spans the base space, and consists of those vectors which are orthogonal to the set German M German minus pi inverse of s squared, which is approximate the fiber. The metric on the fiber is ds squared equals negative u to the negative 1 power dt squared plus 4 script L squared u times d normal psi squared. So the vectors which span V sub q are the fraction with numerator partial differential and denominator partial differential t times a n d times the fraction with numerator partial differential and denominator partial differential normal psi. The metric on the set German M German minus pi inverse of s squared is.
See equation 7-59. Those vectors orthogonal to g bar sub v are colon see equation 7-60. Clearly see the next equation shown. And see the equation. Span the base space. So, if every vector can be decomposed into these two spaces, then see equation 7-61. And we have a local direct sum. Although not orthogonal, partial differential phi minus cosine theta partial differential normal psi and partial differential normal psi do span the subspace spanned by partial differential phi times a and d partial differential normal psi, so every vector can be decomposed. Now, the interesting part of the metric g is contained in g sub v since it corresponds to the part of German M which is not locally inextendable. Taub gave the metric for u of t is greater than 0 in which t equals constant hypersurfaces are spacelike. Newman, Untai and Tamburino gave the region where u of t is less than 0.
See the group of equations. Define y of t equals t squared minus 2mt minus script L squared. Then y prime of t equals 2t minus 2m and y double prime of t equals 2, with 0 crossings at. See the next equation shown. And see the equation. Thus, u of t is greater than 0 right double arrow y of t is less than 0 right double arrow region between t sub minus and t sub plus. U of t is less than 0 right double arrow y of t is greater than 0 right double arrow region to left of t sub minus and right of t sub plus. Figure 7.11. Analysis of u, t. Consider analytic extensions of script f script, g sub v.
See the next equation shown. G sub v has singularities at t equals t sub plus or minus where u equals 0. Consider the manifold defined by normal psi and by t sub minus is less than t sub plus, script f sub 0, g sub v, can be extended by defining see the equation. Similar to Meissner case where log t equals the integral from 2 of the fraction with numerator normal dt and denominator t. The metric becomes, see equation 7-62. This is analytic on script f script prime, with topology s prime times r prime, defined by normal psi prime and negative infinity is less than infinity. As expected t sub minus is less than t sub plus of, script f script prime script, g sub v prime, is isometric with, script f sub 0, g sub v.
We have CTCs in the extended regions. One family of null geodesics crosses both horizons t equals t sub minus and t equals t sub plus, two horizons unlike Meissner's one, but the other family spirals round near these surfaces and is incomplete. Another extension follows from normal psi double prime equals normal psi minus 1 over 2 script L the integral from 2 of the fraction with numerator normal dt and denominator u of t. See the next equation shown. Normal psi prime extension ds squared equals 4 script ld normal psi prime times script lu of td normal psi prime minus dt, and null geodesics d normal psi prime equals 0 right arrow normal psi prime equals constant, and have script lu of td normal psi prime minus dt equals 0 right arrow normal dt over d normal psi prime equals script lu of t.
Figure 7.12. Analysis of characteristics. See the equations. For normal psi double prime extension, ds squared equals 4 script ld normal psi double prime times script lu of td normal psi double prime plus dt. Flip above picture about t-axis. The behavior is very much as with Meissner space. One family of null geodesics in a given extension crosses both horizons t equals t sub minus and t equals t sub plus, but the other family spirals round near these surfaces and is incomplete. To show incompleteness,
see the group of equations shown. Script f sub 0, g sub v, is 0 is less than or equal to normal psi is less than or equal to 4 pi and t sub minus is less than t sub plus with ds squared equals negative u to the negative 1 power dt squared plus 4 script L squared u times d normal psi squared covering space of script f sub 0 is script f sub 0 defined by.
See the equation. Using the above double null form we have the domain. See the next equation shown. Define new coordinates. See the equation. Where see the next equation shown. Thus,
see the group of equations. So see the equation. Thus see the next equation shown. Similarly, see the equation, and see the equations, with see the next equation shown.
And see the group of equations shown. The transformation with u sub plus or minus, v sub plus or minus is to study the structure at infinity. In such a Penrose representation the extension is fairly clear. Covering space of script f sub 0 is script f sub 0 defined by see the equation. On script f sub 0 the metric is written in double null form with see the next equation shown. Penrose transformation.
See the group of equations. Consider u of t nea r times t sub minus. See the equations. Thus, normal psi double prime right arrow negative infinity follows from t right arrow t sub minus. Thus v sub plus or minus right arrow negative pi over 2 normal psi prime right arrow positive infinity follows from t right arrow t sub minus. Thus u sub plus or minus right arrow pi over 2. Similarly for t right arrow t sub plus, we see that the integral from 2 of the fraction with numerator normal dt and denominator u of t right double arrow negative infinity normal psi double prime right arrow positive infinity follows from t right arrow t sub plus. Thus v sub plus or minus right arrow 0.
Normal psi prime right arrow negative infinity follows from t right arrow t sub plus. Thus u sub plus or minus right arrow 0. Now consider the script f sub 0 raised to the power domain. See the equation. With normal psi equals 0 times a and d times normal psi equals 4 pi identified right double arrow so not simply connected, with COVRING of SPAC times ISG of IVEN times BY negative infinity is less than normal psi is less than infinity. In the region T sub minus is less than T sub plus we can use both sets of null coordinates, thus arriving at the double null form for the metric. Also, negative infinity is less than normal psi prime is less than infinity. Negative infinity is less than normal psi double prime is less than infinity. Transforming to a Penrose type representation with coordinates u sub plus, v sub plus, times and of u sub minus, v sub minus, on times script f sub 0 we get the metric g sub v.
See the next equation shown. See the equation. We get see the next equation shown. See the equation. We get see the next equation shown. In the region T sub minus is less than T sub plus times T equals constant hypersurfaces are spacelike. From the extension G sub V prime of 11 it is also clear that T equals T sub plus or minus hypersurfaces are null. Thus, T equals T sub plus hypersurface haze.
See the equation. Normal psi double prime right arrow negative infinity times WH of ILE minus open brace 1 over 2 script L integral from to ... close brace right arrow positive infinity thus normal psi right arrow negative infinity limit figure 7.13. Penrose diagram. On a given space-like surface of the covering space we have negative infinity is less than normal psi is less than infinity, which represents the orbit of a one-dimensional group of isometries, i.e., normal psi equals normal psi plus and 4 pi. Near p sub plus, p sub minus the action of the group is similar to that of the Lorentz group in 2D Minkowski space. See equation 7-63.
Recall our two inequivalent extensions. First consider script f script prime which followed from normal psi prime and letting negative infinity is less than T is less than infinity. If we regard normal psi prime equals normal psi plus 1 over 2 script L the integral from 2 of the fraction with numerator normal dt and denominator u of t once again, but now consider the continuation to T is less than T sub minus and T is greater than T sub plus we find for T is less than T sub minus, we've labled u sub plus or minus of T sub minus equals pi over 2. Consider the values of normal psi prime for T is less than T sub minus.
See the group of equations shown, which works as SU of 2s cubed. SU of 2 are isomorphic, so see the group of equations.
Action of u of 1 on z sub 0, z sub 1. See the next equation shown. With C the equation projects down to theta, phi. See the next equation shown. Grouping forced. So 8 are ranging from 0 right arrow 2 pi sweeps normal psi through all values. Meissner is covered by T is less than negative x region of Minkowski, tilde 1/2. Covering space of X is a pair X, F where X is a connected and locally connected space, and F a continuous mapping of X onto X, such that each point X is a member of X has a neighborhood V of X such that the restriction of F to each connected component C sub proportional to of F inverse of V of X is a homeomorphism from C sub proportional to onto V of X. So, as long as the boost identification is finite each point X is a member of X has a neighborhood V of X such that the restriction of F to each connected component C sub proportional to of F inverse of V of X is a homeomorphism for C sub proportional to onto V of X. Thus Meissner space is covered by half of Minkowski.
7.2.7 Killing vector structure of Taub metric G sub AB. See equation 7-64. With see equation 7-65. If K sub AB is the killing metric on SU, 2, K sub AB equals delta sub ij sigma sub A to the I sigma sub B to the J, and have C equation 7-66. If we write C the equation, then C equation 7-67. Now the set sigma sub A to the I is a right invariant basis for SU, 2, and K sub AB is both left and right invariant under SU, 2, so G sub AB is left invariant under the U, 1, subgroup of SU, 2, that fixes normal psi sub A. Symmetry group of Taub is thus SU2 times U1.